Okay, the class only dropped by 5% after one lecture. That's not bad. There's going to be a bigger dropout after this. Alright, so now we go into the nitty-gritty of this, and you actually discover that this is a lot about statistics and linear algebra and calculus. And they're all good things. Important things to know. The more mathematics you can take, the better. But again, this course will be focusing on practical skills, and the practicals are very important. Nonetheless, if your linear algebra is rusty, I strongly recommend that you Google linear algebra, linear algebra lectures, and you can take Gilbert Strang online, linear algebra lectures, or you can go to, what's that famous instructor? He's really good online. Khan's Academy. He's got brilliant lectures on linear algebra. In case it's rusty, just go back there. And calculus as well. So important things that are essential for taking this course in terms of mathematical background. You have to know what a vector is and what a matrix is. So these are very important skills. Just sort of basic background. If you don't have that basic background, you don't know what a vector or a matrix is, then there's Khan Academy, there's Gilbert Strang lectures, or you can just Google linear algebra, go to Wikipedia, everything is in Wikipedia. That is background for this course. Some very basics of statistics, like for example for next week, we're going to go into Gaussians and multivariate Gaussians. Gaussians in more than one dimension. So they're extremely useful, and so some basics of probability and statistics are essential as well. And again, if you haven't had an introductory course in probability and statistics, again, there's very good ones for the undergrad level online. And finally, calculus. One of the key methods for learning that we will use here is something called gradient descent, which is optimization by going downhill. So, how many of you ski or snowboard? Okay, nice. If this was my class in Vancouver, everyone would be... Actually, the class would be half empty because half of the people would be up on the mountain snowboarding. It's just, learning is just like snowboarding. Just look for the steepest descent and go for it. And so put your foot in front of the board and enjoy. That's pretty much the steepest descent, is in look for where it's really steep and go in that direction. It's like the double black diamond or where they tell you not to go. That's what it's about. Don't take this as advice. Okay. And that's basically, calculus is something called gradients, and you need to know that concept. The derivatives, a lot of the things that we're going to do will be about differentiation. We'll try to build machines, and essentially what we try to do is build machines that we can differentiate. If we can differentiate, we can find their optimum operation. So we can take a Turing machine, and if you can differentiate a Turing machine, if you build a differentiable Turing machine, you can build a Turing machine that learns from data. If you can take a graphics engine, something that generates graphics movies, and you can make it differentiable and you can generate movies. If you can do that with speech, you can generate speech. So basically, if you take any machine, make it differentiable, make it learn from data, and now it can adapt. That machine can adapt to the world. So derivatives are extremely important. Go revise gradients. Gradients are very important. We're going to get into them next, not next week, the week after, but they will be essential. And already I will touch on them today. Okay, so this class now, it's going back to some very basic statistics, and we're going to look at something called linear regression. And we're going to try to understand it, and this is essentially something that's also known as least squares. We're in the setting of what folks call supervised learning, in the sense that there is inputs and there's outputs. And there's the teacher gives you, for each input, shows you what the output should be. If this is an image of a cat, the output should be the label cat, and so on. If this part of speech is say chameleon, the output should be a string of characters that say chameleon, and so on. There's many ways in which, so there's also, in learning any new field, there's language associated with it, there's also parlance. And inputs are often known as covariates, that's in statistics, or they're also known there as predictors. We often call them features, or we call other things features as well, but think of often the inputs are called features. The outputs are variates, things that vary depending on the input. They're called targets. You're trying to learn some target class, or they're known as labels. And I'm sure there's many other words by which these get referred to. But interchangeably, I will probably use these terms. Inputs, outputs. And so, in the first thing, in linear supervised learning, we assume that the relation between the input and the output is linear. So if you are in 1D, it would be a line, in 2D would be a plane, in high dimension would be a plane in high dimensions. But there's a sort of linear relation between the input and the output. Not very exciting, because it's just, a line is just basically saying if you increase the x, increase y, if the slope is positive. But what we learn here will be useful later. And in particular, a lot of processes, basically pretty much everything in life is nonlinear, but if you look at it locally, sometimes it's linear. So by linearizing in a local region, you can actually design very nice machines. For example, machines are able to land automatically from the sky, and you owe your lives to these machines if you've taken a plane before. And so linearization is very useful in engineering. And so knowing how to play with linear models, it turns out to be useful. Also, you'll see that most of these models have as a submodule a linear module. So if you can use linear modules, if you can understand how these submodules work, then you can take advantage of them to build large architectures. Linear models are also nice because I can teach you the basic concepts of statistics with them, because I can do everything by hand. So all we need is a piece of paper to do this. We don't need computers or computing. Later we will not be able to do things by hand, but the same principles about learning that apply to these models that we will discuss next week apply to nonlinear models. So saying here, we'll learn the basic concepts. Okay, so how does it work? So the setup is the following. We're going to give we're going to start introducing some notation here. We're going to be given what I call the training data set, training set. That will contain n instances. So these instances could be pairs of images and their label, the text label that says what the image is about. And so the inputs will be the x's and the labels will be the outputs. Now I will use this notation where x1 colon n basically is a set which includes x1, x2, all the other x's up to xn. So it's just a shorthand notation for all the x's. X that indicates how many there are. Each of these x's could be, for example, a vector with the components, and that's what I mean by this. Here, I just mean a vector of numbers that are essentially d numbers, and those d numbers happen to be real numbers. There could be other things. There could be binary numbers indicating whether you prefer something or not. Categorical variables and so on. But let's say they're just d numbers, or d inputs, the attributes, as they also know, the predictors. the output is going to be the target, and we're going to assume for linear regression, for simplicity, that the output is just going to be one single real number. Okay? The inputs, in a sense, could be integers, there could be other things, but that's sort of not too important. So let's look at an example. An example might be something like this. We're given a table of data, and this is what this data set might look like, where we have the wind speed outside this building, and we have the temperature inside this building, and then what we would like to do, right now what we're doing is we're opening these windows by hand to control the temperature in this room, but imagine that we wanted to improve on that, and we wanted to put an automatic thermostat in this room that would detect how many people walked in the room. So it would know how many people are inside here now. It would know what the temperature outside is because of the wind speed. And then it would automatically predict what is the energy requirement to keep this room at a comfortable temperature. Okay, so in this case, this would be x1, and this would be y1. So I want my model to, given the speed of the wind measured outside by some meteorological station, and given a counter that just counts by some sensor how many people have walked into this room and walked out, and would automatically be able to predict what the setting of the thermostat should be. Okay, so to regulate the temperature so that we're comfortable. Okay, so the inputs are the x's, the output is the y. We would like to learn this model, because if we do learn this model, then this thermostat will solve our problem. It will just adjust the temperature based on how many people are here and based on the temperature outside. And if that works, then we'll be happy than having to open the windows manually. So that's x1. x3 would be this vector. And this would be y3. Okay, so in this case, in particular, d is equal to 2, as you can tell, and there are 4 data set instances. There are four rows of the data set. So that's a simple form, a simple data set. But already, if we could know how to manipulate this data set, we could build useful technology. And so, in particular, as I mentioned, given now a different number of people and given different temperature measured outside on any arbitrary day, I would like to automatically predict what the temperature, what the energy requirement is in the thermostat, so that this room is at a nice temperature. And so, we're going to do this in 2 stages, and this is going to be true of always in supervised learning. So the first stage is going to be called, I will refer to it as training. Statisticians call this statistical estimation and so on. The idea is, given the data, and the data is essentially that table of numbers which has n x's and n y's. The y's are one column, the x's could be several columns, d columns in total. This gets put as an input to what we're going to call the learner. And what we're going to learn is a model. Quite often, and it will be the case in this course, not necessarily always, but certainly in this course, the model will have parameters. So statistics is a very vibrant area for so-called non-parametric statistics. I will not be covering it, but that area is so very big here at Oxford as well. There's people like you, I'd say, in statistics, Michael Osborne in engineering, so on, that all do excellent work in that area. Frank Wood as well, so I recommend you attend their courses if you want to learn about that. But here I will focus on models that have parameters. I will, however, let this number of parameters be very large. So the models will be in a sense non-parametric, in the sense that the parameters could be a billion parameters and so on. The models will be so large that you will not be able to sort the parameters in a machine. You really need a server with several machines, and you need to have some very interesting architectures to be able to, smart architectures to distribute the vector parameters. That's like how most image recognition systems work at companies. You need what people call a parameter server to just handle a single recognition model. I often use the Greek letter theta or theta to describe the model parameters. For linear models, in the simplest form, a line, the parameters are the intercept and the slope. So learning is just computing the intercept and the slope of the line. It's basically learning the plane. If you can learn the plane, you've learned. Once you have the plane, you're going to take a new data point, and this is what I'm going to call testing. Or prediction. So the new data point goes into the predictor. The new data point and the learned parameters go into the predictor, and they generate a prediction. And I'm going to put a hat to indicate a prediction. So the hat denotes prediction, and it's the prediction for that point, which I will write either like this or like write it as a, it's a function of the input. So I could write it like that as well. So the idea is, during training or learning, I can put here learning, we estimate parameters from a data set with n instances, and during prediction we use the estimated parameters, the model that we've learned, to make decisions, to make the forecast. As we will see, this is the first way we're going to do this. As we will see later, this can happen in an online fashion. You're adapting the model as the data is coming. So most of the things that we do have to be adaptive, in fact, on the data, because there's just too much data to load the data to memory. So you really have to learn with small batches of data and be able to update them. And how big the batches should be, that depends on statistical considerations, but it also depends on a lot of systems constraints in terms of communication, access to disk, how much it costs to send things over the net, how much memory does your GPU have, and so on. Okay, so let's look at the first linear model. The first linear model is a line. It has intercept θ1 and slope θ2. The input is just one variable, in this case d is equal to 1, just one column, and then the output is also just one column. When we do learning, we also need to specify what I call an objective function. Objective function. Some people call it an energy, or a loss. It's something that measures how well you're doing. So in supervised learning, you want some function that will tell you whether you've done good learning or not. And let's look at one example. So one example could be, you've done well if the difference between the true data in the training set, so the y's that you have in the training set, are close to the predictions that you make in the training set. So basically you train, you learn theta. Once you do theta, you multiply your thetas times the x in the training, and you compute the y hats. And if your y hats are close to the y's, then that error is going to be about 0. And Gauss came up with this 300 years ago, and it worked for a lot of problems, and it became very popular. It's very analytic, very tractable, and we use it because of that, even though it's very it's dangerous, as I'll soon show you. But basically, graphically, what we're saying we're doing here is we have a function with x-axis x and with the height of the y's, and we're given some data points, and what we are doing is we're fitting a line to these data points. And the way we're fitting this line is we're fitting in a way, like a good way to think about this, we're right across from Robert Hooke's building, so it only befits this place to use springs. And think of Hooke's law, and remember there was a kx squared, the squared, and so one way to think about this, and hence the energy, kx squared, is that if you imagine that each of these red dots, and I should say what these red dots are actually, so the coordinates are basically the data points. So this would be x1, this would be, say, x3. I mean, the data can be scrambled, there's no particular order, so I'm emphasizing that by writing it this way. And this height here is the corresponding height y1, this is the corresponding height y3. So that's the data. The data is these red dots, and those are its coordinates. This line, which is our model, has slope θ2, and the height of the intercept is θ1. Okay. And this difference here is what we want to minimize. If this is y4, height y4, this guy here is the prediction y4. And so this gap here is y4 minus the prediction of y4. And we use squared because we're using springs. We're trying to minimize the energy. We're trying to find a minimum energy configuration for this line. So if you were to, and you can actually implement this with springs if you want. And so basically if I try to twist the line and I let it go, it will sort of converge at one point of minimum energy. And there is only one such point, as we will see soon. And that's essentially how this works. And this works extremely well. A lot of science is based on this, and there's all sorts of things with this. And there's millions of papers out there using this model to describe some sort of data. Turns out to be a very useful model.
We directly wedge the springs. Basically, here we're measuring the distance to the y-coordinate and not the distance to the line. So the springs would have to be somehow made to always stay vertical. Right.
This is very important. That's the first dangerous thing about this model. It's why should we prefer vertical? So anyone looks at this, that's then a bit of computer graphics, we made it, or a bit of common sense, would say, why don't we measure it like this? That would be better. But in school we always see the vertical one, because that's what we learn. So it turns out that this indeed is, people do this way. In the next class we're going to go over and look at measuring things this way. That's going to give rise to total least squares and so on. One of the big problems with these models as well is you might have data that looks like this. Okay, so where you would like your line to be going through the points, but then this fails, because what happens is when you have something that looks like this spring is really stretched. And when you have a spring that's really stretched, even if it's only one spring that's very stretched, it completely destroys the line. You'll end up with a fit to the data that looks like this, just because of that one spring. And that all comes because of our choice of metric. So we will learn other choices throughout the course. And so this is always, something that you need to think about carefully for each problem. What kind of metric should I use? And in fact, coming up with good metrics is one of the most fundamental problems, I think, certainly in the whole scheme of building intelligent machines. I think a big part is learning these good metrics. So if you generalize it to higher dimensions, then you would have, we move on to, instead of just having theta naught plus theta 1 times x1, you would now have many, you have d thetas. So you have x I1 theta 1 plus x I2 theta 2 all the way to xid theta d. So for each data point, the prediction is you would use a plane to make a prediction. And as a convention, we typically set this first guy always to be 1, because then that gives us the offset, so that gives us the bias term. We call it the bias term. So it's basically this guy here. So as you can see, there is a 1 here. That changes the height of the line, the height of the plane. Matrices are great for this because instead of writing all these sums and details, we can just group all the various variables into a single data structure, and we can just manipulate the data structure, because the data structure has all sorts of properties that we've studied for centuries. And so we can write this model, instead of writing it component-wise, instead of expanding it like this, or writing it using these sigma notations, these loops, we can just write it very succinctly in matrix representation this way. And so that basically says that, as you can see, I goes from 1 to n, so you have I1 to In, and x goes from 1 to d, and then you have d parameters. So we can group this in a single. So the linear prediction is you just multiply a matrix of the input data times your vector of parameters, and that gives you the output. Let's look at an example. Back to our thermostat design. So we have two inputs, the wind speed and the people inside the building, and we're trying to predict the adjustment of the thermostat, how much energy needs to be injected into regulating this room. So in this case, as you can see, the y is this vector, so that corresponds to what I've drawn here, and the x, which corresponds to these 4 columns, is what I've put in here. So I've just copied it. So if your data is stored as a table, it's very easy to form these matrices. And then in order to compute the parameters, you need to just multiply this table. Oh, hang on, I haven't told you how to compute the parameters. That's coming soon. But if you want to compute the y's, basically the model is y is equal x theta, you would multiply this x times this vector, and that would give you y. We still don't know how to get the thetas, how to compute the thetas from data. But we already know the loss. We're going to try to minimize quadratic loss, the Gauss loss. And so in particular, let's assume that our theta, suppose someone come and gave you that theta, some learned machine already gives you a theta, then in order to make a prediction on the training set, in order to generate the y-hats from 1 to 4 on the training set, you would basically take the data again, x, and you would multiply by theta. So x times theta, that's going to give you predictions y, and now you get y hat, and now you compare y hat to y, and you sum all those square differences, and that tells you how well you're doing. Okay, so that's how you would make predictions. So once you have a single value of a single vector theta, you can make any predictions. So the question is, how do we get that theta? So this, again, you can those predictions here I should have added. These are predictions on the training set, but ultimately you want to get new data that you have not encountered before in your training set, and you want to make predictions there, and hopefully those predictions will still be good ones. So if I have a new x vector, I add it to that matrix and I multiply times my vector of thetas, and that's how I compute a prediction. This is essentially mathematically the same as evaluating the line at that point. Okay, so just like I vectorized the description of a line, instead of using the sum or a loop in code, I'm going to use just direct operation. So this is important not only to shorten the math and in order to derive things more quickly, but this is also essential to get code that runs fast. You have to vectorize code and be doing lots of loops. Because we have very good libraries these days to deal with matrix operations, so we can take advantage of that. The quadratic form, the sum of square losses, can be very compactly written as this. And to see that, the first thing you should note is that if you have a vector, here I'm using bold for vectors, by the way, and non-bold for scalars. And so matrices are typically capitals in bold. So this is a matrix times a vector. I'll use a bar when I write. And so to see that this is true, well, if you have vectors, if you have a vector x that has entries x1 and x2, and a vector that has entries y1 and y2, then you know that x transpose, actually let me transpose these. So x transpose y is just x1, x2, y1, y2, and that's just equal to x1, y1 plus x2, y2, and that's equal to sum over I, xi, about the transpose, xi, yi. Okay, and so it's a trivial exercise for you to then go and rewrite this as this, because essentially if you, let's say, look at this, what we have here is a vector of y1 all the way to yn minus, and then you could write each of these is x1 transpose, x2 transpose, all the way up to xn transpose. Each of these x vectors has the components, and it multiplies the vector theta, which is in this case a vector with one component. So that corresponds to so this term corresponds to this term here. I'm going to let you fill in the remaining steps. You can to convince yourself that you can rewrite this expression in matrix vector in that form much more efficiently. So the dot product, as you can see here, what I'm doing is I'm taking a dot product between this vector and this vector, which is the reason why I get the squared here. If it's the same vector, x dot x transpose x is just the sum of the xi squared. And then I just need to break this into its various components to actually identify the vector. And so from now on, I'm going to use this form, because it turns out that this form is a lot easier to manipulate than to be using these sums and these loops. Now, you can also plot this function. Like, for example, if my theta is two-dimensional, so in other words, I only have two parameters in the model, theta1, theta2, so back to the line, intercept and slope. Or maybe I choose not to have an intercept and I have a plane going through the origin, and then I just need to choose its two angles, theta 1 and theta 2. This is a quadratic function, so it's a ball. Okay. And in fact, it's a ball, and if I were to cut it, if I were to slice it, from what I would get is ellipses. So these guys at which the height is the same, these curves here, these are the contoured curves. These are the lines at which you're at the same height, you're at the same cost. So if you follow this line, your cost doesn't change, you're always at the same cost. Your objective is to go to a lower cost. So learning is about doing this. Most important thing I've said today. It's the snowboarding thing. If you go perpendicular to these lines, if the lines are the constant height, if you go perpendicular to this line, that you pick in the direction of steepest descent. Actually, the gradient is this mathematical function. It's a vector of derivatives of this function. A vector of derivatives, and it exists at every point. These little arrows here in blue, these are the gradients. The gradients point outward. You go in the opposite direction of the gradient when you go to the minimum. If you want to go to the if the function is flipped and there's a maximum, which usually happens with probabilities, you want to maximize probabilities, you follow the gradient to the top. And that's essentially what we're going to do all the time, follow gradients, up and down. And that's going to be our mechanism for learning. If we know that the loss is this ball, then we know a ball only has one point, that is the optimum point down here. So we know if we follow the gradient, if you go downhill, you're going to get there. It's impossible to get anywhere else. With a bit of math, you could formalize the proof now that you have the intuition. It turns out, well, so then to find a solution, to find the optimal theta, is just a matter of differentiating. So you can do it in two ways, like in this case. What I would do is I would take the derivative of this, I would take the derivative of j of theta with respect to theta 1, and then I would take the derivative of j of theta with respect to theta 2. Okay. This would give me some function with an equation with two variables. This would give me another equation with two variables, two unknowns. So basically a function of with two equations with two unknowns. These are called the normal equations. They are described at length in the Wikipedia page. So if you do least squares, if you Google least squares wiki, you'll get the details of how you would do this. It's very tedious. I'm not going to do it this way. I'm not going to make you go through this painful exercise. There is a fast way. You Google matrix differentiation, and you learn that you can differentiate with respect to matrices and vectors, and you spend some time learning these rules, and you learn that, oh, the derivative of a matrix times a vector is just a matrix transpose, and for a quadratic this is the expression. And then you realize that there's a field of algebra called matrix differentiation, which has Kronecker products, has all of these things. We're not going to need to go and look into that, but I can tell you that the basic data structure of the language we'll use in this course, Torch, is a tensor. And so it really helps you to learn a little bit about this. So Google matrix differentiation. There's very nice Wikipedia pages on this. And the nice thing about this is it allows you to do things quickly. Instead of me trying to solve all these equations, figure out how to solve them, I can just look at the derivative with respect to the entire vector of the expression of the cost, and what I can do is I can expand it by just multiplying terms, and I have minus 2 y transpose x theta plus theta transpose x theta. So this is where linear algebra comes in. You need to remember what transpose are and how to multiply matrices and so on, and how to invert matrices, never divide by matrices, that sort of thing. Very essential. So basics of linear algebra are useful. But once you have them, you can do these calculations very quickly. And oh, by the way, who knows why I grouped the two terms, the two cross terms, into a single term?
It's a scalar.
It's a scalar. Another very important thing to do is always keep track of the dimensions, both in the code and when you do math. Always keep track of dimensions.
On that topic, you need a transpose after the penultimate x on that equation.
There you go. I would have got it by looking at the dimensions. So these are the dimensions of each of these quantities. Keep track of them.
Nando, I'm sorry to interrupt, but your x's are column vectors, but when they're in the matrix, they're as rows. Is that correct? Because it's very easy.
I think the way I define them, and it varies according to the lecture. I think I've defined them this way. Because I wrote them initially as rows. It's all about definition. If I define them to be rows, then like that I'm defining them to be vectors, so I have to transpose to make them rows. And if I define them as columns, then, but that's a good point. If sometimes those things are not clear, just let me know, and we'll fix those transposes. And then if you do this, then you apply the rules of differentiation. You get 0, you get minus 2 x transpose y, and then you get plus x transpose x theta. We equate to 0, and then we get that theta is equal to x transpose x inverse x transpose y. And that is the solution. So you can calculate this very easy. So if you have the tables, in Torch you'd have the tensor, you just transpose it, multiply, invert that, multiply times x, multiply by the vector of y's, and that's theta. That's how you learn. So in this case you don't need to follow gradients. I can do this by hand. That's why linear models are popular, because we can do them by hand. One problem with this is it requires that you load all the data. So this is easy until you have to invert a matrix that's a billion by a billion, and this approach sort of collapses. And then the other problem is a lot of the times this matrix is rank deficient, so you will not be able to invert it. Very quickly to finish this lecture, so we will be using Torch 7. So you can Google Torch 7, that's what we'll use for this course. Basically because every neural network that we'll discuss in this course is already implemented there. You can reuse it, you can do new things with it. It's a very nice library to manipulate this. And as I mentioned, it's a library that is heavily used at, I think some of the companies are sort of doing groundbreaking work in machine learning. So if your intention is to get a job in one of those, then I strongly suggest you learn this. And also because it's a new language for everyone, this is, for those of you who have a background in neuroscience or mathematics and you're learning to program, this is a very easy language to learn. And it has very little in it. It's an extremely dangerous language though, but it's one that's very easy to learn. Brandon will be doing the exercises pointing out the dangers. But so in Torch, the first thing you would do if you're doing, like in this case, we're trying to predict corn yield based on amount of fertilizer and insecticide. You would load the data. I will make these slides available, so you will have these links, so you can actually, this tutorial exists online. You load the data, you basically form a matrix, or in this case a tensor, which is an outer product of two vectors. You could scale this to higher d, because like a video has x, y, and z. So we like tensors because we like to look at data that has more than just 2 facets, that has many possible facets. Like a video has 3, but you could imagine that a lot of data, like in recommendation and so on, could have easily 1,000 facets and so on. So it's good to manipulate tensors. This is how easy you build that model. You basically say the model is sequential. We're going to do this as a neural network. It's going to have inputs x1 to xd. Each input will be feeding into a linear, what our sort of really abstract model of what a neuron is, computational unit that is linear, and that's going to make a prediction y hat. And basically it has 2 inputs. It has 1 output. That's how you specify the model. When you specify the model like this, Torch knows that you're talking about this model. That's linear regression seen as a neural network. From a neural network perspective, it's just a single unit that has a linear response to the input. And each of these things here is basically weighted by a parameter. And typically in Torch, even though it's not made explicit here, one of the inputs x1 will be set to 1, so you'll have a bias term. So you'll end up, when you specify the model like this, it automatically generates for you a vector with 3 parameters. You then need to specify the training objective, like in this case, the squared loss, the quadratic loss, and so it's just y minus y hat squared. And finally, you need to compute the parameters, and it does not do the exact solution like we did. It will follow gradients. So Torch will do this. It will go downhill by taking little steps, and we'll visit each data point, like each group, small groups of data points, and we'll follow the gradients. And so we're going to, in the following lecture, we're going to play more with the models. We try to go non-linear. We're going to look at statistical problems, things like cross-validation and so on. And in the week after, that's when I'm going to spend all the time looking at optimization, gradients, Hessians, and how we use optimization to get here or here. Sometimes here is really good too. So we don't always get to the... But typically your learning problems in reality are like this. They're not balls. That's what we encounter. We try to convert them to balls, but they tend to be like this. All right, thank you very much.